Again, we're going to talk about the format of the problem. The reason why I think it's a good idea to record it and put it in the discussion board so that people who come in late, like the people who are working today, since this is an extra session, is so that they benefit from the same thing. Again, we're moving the discussion to Canvas. We're going to be talking about basically some key ideas. The biggest question, and I think it's a valid concern question actually, is we have to master those sign conventions. Whether we're calculating the electric field, the magnetic field due to a charge, due to a current, whether we're calculating the force exerted by by a magnetic field on a wire, or a magnetic field on a charge, or basically a magnetic field on a loop. All of these problems we have to have a full understanding into the sign conventions when you're using the right-hand rule. Now, if you don't want to deal with the sign, and if you don't want to use the right-hand rule, you have to be extremely good at two things. First of all, basically drawing your system of axes, namely the x-axis, the y-axis, and the z-axis correctly, and putting all of the things that are given to you. If it's a magnetic field, then you know its direction, put it in its proper direction. If it's a force that was given to you, put it in its proper direction. If it's a velocity that was given to you, put it in its proper direction. Whatever is given in the problem, if it's a current going through a wire, that is the direction for that current. So basically, when you do a vector like this one, you don't have to worry about the right-hand rule. Basically, just use the proper cross products in the right places, and the directions should solve themselves by themselves. That too applies actually to chapter 30, which is not in this exam, namely for the EMF or Faraday's law, but then you will be dealing with the same. If you don't want to use the right-hand rule or Lenz law, trying to figure out which direction the EMF is going to be going for the current and so on and so forth, as long as you have the direction of the magnetic field, the direction of the area that is enclosed by the wire you have a current in, or the current is going to be induced in. So basically, if you have all of these directions correctly and you have the system of axes again properly oriented, then you're fine. You don't have to worry about this. But again, I guess we probably will move the discussion in there, and I will talk about that, because that's a major headache. If you don't get your signs correctly, the rest of the calculations probably will be wrong. Especially, if there is something that depends later on that calculation, that is going to be wrong. The whole thing basically collapsed before your eyes, and that's because something went wrong way from the beginning. So basically, we have to figure that out. We have to talk about that. But also, like I said, before we started recording this thing, there are some problems of specific interest that I picked up from the homework basically set, that I thought will illustrate this point and go in much deeper detail. And I can again talk to you about this problem since we're recording this session. And I'm hoping that the people who are not here look at these problems again and make sure that they have full understanding of how to work out these things and have a deep understanding of these things. And the problems I was thinking about are, problems 62 and 65 from chapter 27. Problems 65 and 68 from chapter 28, that's 65 and 68, and then problems 69 and 70 from chapter 29. As a matter of fact, some of problems from chapter 27 all the way to 29, they have a flaw in them, and the flaw can be adjusted with chapter 30. Then, because we're not getting there yet with it, so we're probably going to leave some of those things, namely the fact that these things can induce EMFs, things can go a little bit different, and things like that. Anyway, we will discuss these things in more detail when we talk about these things on the discussion and on Canvas. And that's it, basically. And unless you guys have any quick questions right now that probably we can talk about, we probably are going to move the whole thing into Canvas.
One thing I was wondering, I wasn't here yesterday. When is the test?
The test is going to be on Tuesday. At the regular time, 11 o'clock, basically the questions will be on Canvas. You will have the exam will be divided into two sections. The first section, basically here is your problems that you're going to be working on. Let's say, for example, it has two parts, that problem, part A and part B. Part A, you're going to come back into this question and enter the numerical value there or the symbolic value in there that is asked from that question. So you work out your problem on your piece of paper, and then you go back and you enter the value in there. You work out the second problem, the second question, and then you enter the numerical value in there. Now you're done with problem one. You can go to problem two, or you can choose to start with problem two and do problem one later on. So basically, that is trying to mimic basically the exam in the classroom. Now, when you're done with all of this, there is another part actually of the exam for file upload, meaning your work that you did, that's the one that you answered on, you need to upload it back to Canvas basically by taking a picture of it. You don't need to do PDF. You don't need to go out of your own way to basically do what you need to do. I need that work before a full grade for that exam. So you need to answer. Remember, you'll get credit also for your showing the work, and actually that's going to be a requirement. It's not an option. You're going to upload your work back into Canvas, and that's why the time allotted for the exam is more than an hour and 15 minutes, the normal class time. You will be given an additional time, which is equivalent to the class time, to figure out basically a way of doing a good picture of it and sending it right there. And it has a time limit. Please do it before the timeline. Now, if you cannot, for some reason, upload it to Canvas, you need to email it to me somehow. It has to be before the deadline, before the due date. Now, that is basically one thing as far as this exam. You need to know, extremely important, that everyone is aware of the fact that none of you guys have similar numbers. So you need to basically, I'm going to use a random generator so that every person, he or she has different numbers than anybody else. So at the end of the day, your answers will be different than anybody else. And basically, if you choose to start going around and things like that, you're going to waste valuable time, and you don't want to do that. So the thing with it is, you need to go focus on the review problem, which was 18 problems, because we have 10 from chapter 27, 10 from chapter 28, and 8 from chapter 29. They have 18 problems. Focus on them, have a full understanding of how these things work, all of these problems, how they work, and the exam should not be outside of those ideas that are from this 18 problems part of the review exam. Does this answer your question, John?
Yes, thank you.
Okay, very good. So basically, right now it's 9:15. We're supposed to start this session at 9 o'clock. And for basically, because we don't have a lot of audience, and like I said, I have these problems, I'm going to go back onto Canvas, and I have a full discussion of how these problems are working. And I'm going to upload this video on that discussion session, basically, that I'm going to create shortly. Do you have any question, Winter, for me?
I was gonna request that we do a problem, maybe, do it on Canvas, but what I was wondering if we could do, I think it's from 28, and that is number 62. I think it's supposed to be simple, but I'm not sure how it looks graphically, so I wasn't sure how to graph the B field. With the magnetic field, it tells you to go ahead and graph it, but
Okay.
I wasn't sure how that works.
Chapter 28, problem 62. Is that what you're saying? Let me try to see what that problem is.
Uh-huh.
Okay.
Oh, yeah.
Okay, let me share this screen with you guys quickly. I know this is the PDF thing that I have. Hold on. Let me go back. So this is the problem you're talking about? 62? Winter?
Yeah, that's the one.
Okay. So what we have in this picture, we have two long wires. the top wire has a current coming out, and the inner wire, the bottom wire has a current going in, okay? And that's a cut from them, basically. This is long wires going into and out of the screen. So each one is carrying a current I, but in opposite direction. So the two currents are going in opposite direction. Okay. Copy the diagram and draw vectors to show the B field at each point, P. So the point P basically is somewhere in the middle axis at the distance A from each charge, from each current, I'm sorry, and at distance X on the horizontal direction. So A vertically and X horizontally. Now, the B field, from the top wire, the B field, the wire is coming out. So the B field now needs to curl around so that, let me get my comment tool in here so that we see the direction of. So this is basically where the direction from the top one, okay, from the positive direction, correct? Cancel. What am I doing in here? I want to just remove the commenting thing. Okay, so do you see it? Because it's curling, in this case, counterclockwise, because my current is coming out of the screen. In the bottom one, it's actually opposite to it. So in the bottom one, it's going like this. You see that? So the magnetic field is going to actually be perpendicular to both of this. Let me show you. It's going to be perpendicular to the current. And since the currents are perpendicular to the screen, so the magnetic field is going to be on the screen somewhere. But it's going to be perpendicular from the top one to this line that joins the points where the current is coming from to the point P. There's going to be a vector in this direction. So that is the B coming from the plus. And again, it's curling this way. The B from the bottom is going to be the same thing. It's going to be perpendicular to this line. Every time I try to draw, it's perpendicular to this line, and it's also on the same on the screen itself, because the current is going into the screen, and since the B that is produced by that current must be perpendicular to the current, it must be somewhere on the screen. You see that? And because of that, it must be also perpendicular to that line itself too. So that is the line that is perpendicular to this line, and also perpendicular to the screen, following the right-hand rule. It has to be pointing down by the right rule, because it's so that's the B from the bottom. Obviously, the two components in this direction, they cancel, in the Y direction they cancel, and the two components in the X direction, they add up. So all you need is just one of them, because the currents are the same. The distance is just the square root of A squared plus X squared. That is this distance. And then don't forget the cosine of this angle, because you're the cosine of this angle. And that angle must be, hold on, the complement of this angle. So because this angle plus that angle is 90 degrees, because this is a 90-degree angle. And this one is, so this angle is this one actually. So the cosine of the whole thing is this angle. So that's cosine of that. And the cosine of this angle is A over that distance. A over square root of A squared plus X squared. So but you have two components of it in the Y direction, in the X direction, and you have no components by symmetry for the Y direction. Does this make sense?
Yeah. So what exactly does the angle tell you about the problem?
There is a symmetry in this problem. Okay. Okay, so the magnetic field due to this current, and the other one is going to be identical, except the Y components cancel and the X components add up basically, and they're the same Y value. So this distance, I'm using this lousy tool in here using the mouse on it. So this distance is square root of X squared plus A squared, correct? This is a right angle triangle.
Yes.
Okay. This is the direction of B from the top. The other one is identical in magnitude, because the magnetic field is, what is it, 2 pi, mu naught times I divided by 2 pi. times the distance, and here is the distance, okay, for this infinite wire. Now we have that, but this is its direction. This is the direction of B, so we know its magnitude. Now we have to multiply by cosine of this angle to find it in the x direction. So this is the bx, cosine of this theta. And cosine of this theta is actually this angle too, because this one plus this guy is 90 degrees. And this one plus that one is 90 degrees. So this is actually the angle theta, basically. Okay, and you can make argument based on the components that are perpendicular and all of that. This side of this theta and this side of the angle, they are perpendicular. And this side of theta and this side of the other angle are perpendicular. So these two angles, and there's a theorem from geometry from a long time ago that two angles have each side perpendicular to the other side. They are basically the same angle. Anyway, this is theta, this is theta. Because we need its cosine, that's why we need to find what theta is. And its cosine is just A divided by this R. So in other words, you will have the expression is going to involve for the magnetic field in this direction, mu naught times this current I times, divided by square root of x squared plus a squared twice, because one of them is coming from the cosine and one of them is coming from the formula for the magnetic field. So it's going to be a squared plus x squared. And in the numerator, we'll have an a coming from the cosine. Because you have two of them, it's going to be 2 times the whole thing. Because you will have one coming from the top part and one coming from the negative part. And this direction is 0. So the magnetic field is going to be in the positive direction. It's going to be this direction, which is D. It's going to be basically 2 times this bx. Okay? Derive an expression for the magnetic field and then graph the magnetic field at a point on the x-axis. So basically now you're going to have a function of x. And you're going to graph this function as a function of x. And as x is equal to 0, this will be value which is a over a squared. It's going to be 1 over a. And as x goes to infinity, this will become 1 over x squared basically. So it's going to drop exponentially. Yes? Yes? So basically this is in a nutshell how it looks like. I'm trying to get GeoGebra to draw this function for me. I'm going to take just the main thing. Oh man, still not. Okay, let me stop this sharing in here and get you GeoGebra. So basically the magnetic field in the x direction is B divided by some B naught value that has to do with A and all of that. So at the end of the day, the function I want to really draw is this function. And then you have the square root of basically, what is it? X squared plus 1. Okay. So the magnetic field has a finite value at the origin. Remember, x can be positive or negative, so we're going to go on both sides. It's always positive, this value for the magnetic field. And it's going to point in this direction. So that's basically the strength of the magnetic field. It's going to drop to 0 at the end, not exponentially, of course, but as a power law. So that's basically how the graph looks like. If you're looking just on the right-hand side, just look at the right-hand side that make x greater than 0. So that's really the graph that we focused on. Okay?
That makes sense.
Okay. So basically, we're going to have more discussion on Canvas. So we probably, I'm going to basically post this one also on that discussion board. Oh, my computer is dying. Sorry. Okay. And we're going to continue the discussion there for all the other problems. That sounds good?
Okay. Yeah, it sounds good.
Yeah, thank you, DJ.
Thank
No
you.
problem. Thank you, guys. Okay, bye.
Bye.